Okay, so hi everyone. Welcome to the 50th episode of the SFU Sports Analytics Virtual Seminar Series. Today we are lucky to have Associate Professor Grant Duthie from the Australian Catholic University in Strathfield, which is in the Metro Sydney area. So it's Thursday for Grant, and so we're lucky to like we're able to make the time zones work out. The title of his talk is Empowering Athletes and Coaches, How AI and Portable Biomechanics Labs Are Transforming Sports Science. Associate Professor Duthie has a distinguished background in elite sport, including roles at the 2000 Sydney Olympics and consulting to high-performance sporting organizations, including FIFA and the National Rugby League in Australia. An expert in team sport player tracking data, he leads the Graduate Certificate in Sports Analytics at ACU and supervises PhD research projects focused on advancing sport technology and performance. With a PhD in exercise physiology from the University of Queensland, Associate Prof. Duthie combines academic expertise with industry-driven insights to benefit high-profile sporting organizations worldwide. So in his talk today, he'll explore the transformative impact of artificial intelligence and portable biomechanics technologies in sports science. Specifically, he will highlight advances in markerless motion capture systems that have accelerated biomechanical analyses and created accessible software tools such as ViewMotion and Slinger. These apps enable real-time feedback for enhancing athletic performance by addressing challenges in accuracy through initiatives like FIFA's Electronic Performance Tracking Systems certification. Markerless motion capture is becoming continually refined. Moving forward, these applications will assist in the areas of injury prevention, rehabilitation, and player tracking, underscoring the importance of integrating cutting-edge solutions to optimize athlete performance through accessibility to sports science applications. And with that, I'm going to hand it over to you, Dr. Duthie, if you can just share your screen, and we look forward to your talk. Thank you for being here.
No worries, mate. Just sent you a request to share.
Yep.
Yep, I think it's good now. And let me just go to presentation mode. Okay, can you see my slideshow, Dave?
Yep, perfect.
Thank you. Thank you for the opportunity to come along, and thanks for the nice words, Dave. As a bit of an introduction, apologies first up. It's summer here in Australia, and unfortunately, people have to mow their grass twice a week almost because it's growing that rapidly, and the people outside have just started up the mowers. So if there's a bit of background noise, I apologise, but we'll work through that. All right. So like Dave said, we're going to talk about how basically AI is becoming a bit of a trend at the moment, and certainly in sports science, it's growing quite rapidly. And really, it's creating a bit of a niche area in the biomechanics space. And I'll talk about how it's making things more efficient, more accessible, and how that relates, I guess, to what Dave wanted me to talk about. This is an analytics group. It's basically resulting in a rapid increase in the volume of data that we're getting access to. That's beneficial for athletes. It's also beneficial for people hopefully on this call that use that data to do analytical analysis processes. We've got a nice new biomechanics lab out at our Blackdown Exercise and Sports Technology Hub. So I've kind of got two campuses that I work out of. So this new campus has been developed. We've got an indoor running track, as you can see here. We've got in-ground force plates over about 10 meters, Vicon cameras. So a new fantastic biomechanics lab that's probably one of the leading ones in Australia and the Southern Hemisphere. The other thing, I guess my background, I'll talk about it more strength and conditioning, but I've always had a bit of a nerdy side. And my first exposure to AI was probably watching the Terminator movies back in the mid 80s, as probably some of you on this call have seen before. So probably got a bit scared of AI initially, but hopefully I've now embraced it a bit more. So just like I said, as a background, I'm probably more came from the strength and conditioning aspect. After I finished my undergraduate, I really went into the coaching space a bit more and worked after completing my PhD. Worked as a strength and conditioning coach in the rugby codes, so both rugby union and rugby league. I'm not sure if you guys know the difference, but there is a little bit of a difference. But certainly very popular sports in Australia and throughout Europe. So I got some time overseas as well, working with those sports. Came back to Australia, kept my links with sporting bodies, but then moved into academia and probably moving into my 10th year now, being in an academic setting, doing research and teaching as well. So my research interests initially started with quantifying the physical demands of team sports. So that's where my PhD was over 20 years ago now. So that was really the start of it. Then after working as a coach in the sport, with various sports, I realized that the technology was developing rapidly, and there was opportunities to do research through PhD students, etc., using technology. And the common one that we have in Australia is GPS systems. So I'm not sure what the rules are in America, but certainly in Australia, in the rugby codes, all the football codes, they wear GPS systems, global positioning systems. So we're getting data. We've been doing that for close to 20 years now. There's also local positioning systems that sometimes get used within the indoor stadiums and smart camera technology, so your optical tracking systems. That really led to me being involved with the FIFA project, which I'll discuss in some further slides. And more recently, the development of markerless motion capture for assessing sports techniques. And I'll do little slides on each of those. So as a bit of a background, my PhD was in physiology, but I always had a strong interest in biomechanics. Now, biomechanics always was a very time-consuming process. So, again, I'm not sure of the people's background on the call here, but biomechanics generally took place either in a lab or in the field. And I'll talk about the lab-based ones here, where we have devices or technology such as force plates, and just in the lab we may have in-ground force plates, so they're within the ground, so people can do movement over the ground and we can look at the force they're applying to it, as opposed to there are force plates that are portable that you can use for your jumping technique, etc. Not talking about those so much here. I'm talking about those in-ground force plates, so if people can do their natural gait movements over them, we can collect data on that. And those force plates sample at high rates and they're known to be very accurate, and you can get 3D analysis from the 1000 hertz data. In addition to that, we have high-speed cameras, not the Vicon cameras I've got detailed there. I'll speak about them in a moment, but just high-speed cameras that have a high frame rate, so we can analyze technique, the footage at a very high speed if we're doing movements, such as some of the work we've done with like kicking a football. Where is the foot contact on the ball? To do that, you can use a high-speed camera, and obviously you get a very good definitive type picture of where the foot is contacting the ball. So they sample at high rates as well. To do the analysis of that, though, requires a lot of manual digitization, rolling through the video. You can digitize it manually, but very time-consuming to do that. The other type of cameras we have are the ones I've got pictured here are Vicon cameras, and we have them both set up around the lab, and we can also take them externally on tripods. Vicon cameras you might have seen before have little reflective markers, so they're little balls that you can put on the body, and the camera sends out a light. It bounces off those reflective markers and back to the camera. And once you've got 3 cameras, you can then triangulate where that marker is in space. Obviously, we get more cameras. You need a minimum of 3 picking up the marker, but the more cameras it picks up, the more accurate it can be. We use sample rates of around 250 hertz, and we're known to get sub-millimeter accuracy with the Vicon markers. So you can see here the markers on a body, someone moving, and we can then represent that in movement. You can do whole body, you can do certain limbs limbs, etc. The processing behind Vicon is actually quite quick. The setup takes a lot of time in regards to putting the markers on the person and setting them up. Once you are collecting the data, as long as the capture, what we call a clean capture, is achieved, then the processing, the software is quite quick in analyzing the data and outputting the data. But there is an extensive setup, and it's very time consuming to do that setup. We can then go to more field-based biomechanics analysis. And this is seen as being more applied and more specific to the sporting movements because it happens in the real world. It's not in the lab where you're trying to replicate sports movements. It's out in the field and you're analyzing athletes doing the technique and providing feedback. Again, we can use high-speed cameras to process the footage of the person or the athlete doing movements. We can have some calibration markers around the space, and those calibration markers can then be used to try and replicate some 3D type analysis of the technique. However, it is very tedious. So it requires manual processing of the video. Basically, a video is multiple pictures over time. So you process a frame, go to the next frame, process it. So, for example, we used to do some sprint analysis where the athletes would run down the track. We would have a black and white tape that had a different color every meter. We could use high-speed video to look at the person running over the 100 meters. We could look at where their steps were. We could digitize the video based on the black and white tape that we had next to the track and get stride length, where their foot contacted the ground along the track. We have time as well because it's a consistent time, so we could get stride rate, the rate that they're running at. But to process that video took somewhat like a fortnight, so 2 weeks of processing to do that one sprint to give that feedback to the coach. Okay, so very labor intensive. The great thing is it's real world, so it's happening in their training environment, it's happening in competition. So we can do that analysis and get that real world feedback. So I guess what I'm saying is that biomechanics used to take a lot of time and it was very tedious and probably boring. And there was a lot of manual labor that went into it and probably detracted a lot of people from going into biomechanics because of the time that it took. Certainly there's a lot of maths and that behind it. But the time, it was just such a labor intensive type of analysis. So what's the future of biomechanical analysis? Well, over the past 10 years, this whole development of artificial intelligence means that the manual labor of processing the video can be done by someone else, and that someone else is a computer. And that can be done at a lot faster rate than what humans can do. So images from our phones, our smartphones, iPhones, or just GoPro videos, etc., can be processed. And we have many sources of these footage now. So not only has artificial intelligence started to increase, but our access to images and cameras, like the quality on an iPhone, the latest iPhone 16, the camera on that is far superior than the cameras we used to have, 10 years ago. Those cameras are ridiculous with the quality they can get now. So we get high quality images and we have computers that can process those images. And there's various AI models that have been developed to process these images, and a lot of them are free and accessible, OpenPose, Deep Cut Lab, or they can be closed source. So industry partners can develop their own type of AI to process certain images. And you can see pose recognition. It's basically looking at the picture and digitizing it using artificial intelligence, as opposed to the manual digitization that humans used to have to do. So I guess this was my first kind of introduction. I got approached by a company called GameFace. They wanted to do some validation because that is the question that comes up for a lot of companies that are using AI to process video and do some type of analysis. I'll say this up front. A lot of these companies are doing this to make money. That's what they're doing. They're developing these applications so that people with iPhones download the app, capture some video, do some processing, and get some feedback. And that's exactly what this company is. So GameFace AI developed a tennis application where you could set up on a tripod your iPhone or Android. I don't think it mattered what type of phone it was, to basically provide a fast analysis of your tennis stroke, to give you feedback on your weight transfer, your power, where you hit the ball on the racket, the racket head speed, for example. So it was a basic application, set up, video yourself at your tennis training, and you'll get analysis of all the strokes, etc., that you've done, and the quality of the strokes. But the first thing that came back was, well, how accurate is this? You're providing all these numbers. How accurate are you? And so that's where GameFace AI reached out to me, and they said, oh, can you do a validation? And I hadn't done any markerless motion capture validation before. I was probably had done more with the FIFA study that I'll talk about in a moment that didn't involve skeletal type tracking. But I said, yes, we'll give it a go. Let's do it. Let's do a study. So I realized all their calculations are based off pose, for example, OpenSim analysis to establish the key landmarks on the body. That's all it does. It processes the image and finds the key landmarks: shoulders, elbows, knees, does eyes, ears, etc. It finds those in the image and where they are in space. Then all the variables that they provide are simply a calculation. So what I realized was that Vicon, what I talked about before in the lab, is the same thing. It has key landmarks and it finds them in space. We just know that Vicon has an accuracy, a sub-millimeter accuracy, and it has a high sample rate to up to, like, we use 250 hertz for a lot of our analysis. Can go higher, but we use 250. Cameras generally capture at around 25 hertz or 25 frames per second. So they're a lower sample rate. They can go higher, but generally the ones on your phone are sampling around the 25 frames per second mark. So what I needed to do, and what I worked out, was that, well, if they're calculating all these variables off the pose, if the pose analysis is wrong, if they're not picking up the key landmarks, then all their subsequent calculations won't be correct. They've got to get the basics right. They've got to be picking up those landmarks. So the first kind of rough study that we did was to compare Vicon data with the data that they're outputting. They're outputting XY data from their pose analysis. I'm getting XYZ analysis from Vicon. And I briefly mentioned to Dave before I got on this presentation that it's sports analytics, but I feel that my analytics is very simple. Most of my analytics is cleaning data and getting data ready for the analytics or the analysis part. 95% of the time is just cleaning the data. So that was the major part that I had to do: synchronize the data and align, which I'll step through in a minute because I know this is an analytics group and I've detailed that. What we found was they had basically less than 5% error in tracking the landmarks in space. So that was a great sign. That was a great kind of start for us in the markerless motion capture space. This was somewhat now 8 years ago that this work was done. And obviously the technology has developed exponentially since then. So but our initial analysis showed about 5% error. The great thing was that it's instantaneous feedback. They can basically go and do some tennis strokes, do a minute of data collection on all their tennis strokes, walk over, process, and it's basically the feedback's there. Vicon, we still look at, well, I call 10 hours processing. There's probably 5 hours of setup in getting the lab set up. Then your data collection was probably about another hour or 2 hours of data collection, and then outputting and processing the data, probably another couple of hours there. So roughly about 10 hours of processing for Vicon. So there's a big difference in the turnaround of the data. Okay, so here's my attempt at pumping up the analytics that I do, although you will see that most of it's cleaning. So Vicon spits out for each of the landmarks on the body that we identify with those markers. It provides me with those XYZ coordinates in millimeters of those landmarks. So the first thing I need to do, and I use the R programming language. Apologies, embarrassing if we're going more down the Python space. I know I need to learn it, and I'm attempting to transfer over. So I read it in. I have to split by landmark. So each of those landmarks has XYZ millimeters at 250 hertz. So they're quite big data files. So I need to go through each landmark. I export individual CSV files of all those XYZ coordinates of each landmark for each trial. Then I do the same for game face. So the Slinger application, they have XY coordinates of each of the individual landmarks. So I have to read that file in, again, split by each of the landmarks that they've identified. Here's my upsampling, analytics, cleaning type analysis. They've collected at 25 frames per second. I need to upsample to 100 hertz. I forgot to say, I downsample Vicon to 100 hertz as well, just to find some middle ground that we're going to compare the data with. Then I export individual CSVs of those XY coordinates for each of those trials. So now I have Vicon for participant 1, the shoulder, during the first 1 minute of tennis strokes. And I have game face, shoulder for participant 1 for that first 1 minute. And I know they're going to be aligned. They're the two data sets that I need to align. The first thing I need to do is synchronize in time. So I need to synchronize in time and space. Time is the first thing that I need to synchronize. Otherwise, I won't be able to synchronize in space because I need to match them up for temporal alignment. So to do that, I calculate the speed of the landmark. So I could be anywhere in space, like moving around in these XYZ coordinates. If I calculate speed, basically the change in that position over time, I can then align them in time because speed is vectorless as opposed to velocity. Velocity, you would have velocity in the X coordinate, velocity in the Y coordinate, velocity in the Z coordinate for Vicon. But if I calculate just an overall speed in the XYZ, I've got speed. I could calculate a vector if I wanted, but it doesn't matter. I'm not worried about that at the moment. I'm just worried about the speed of that landmark. And I also do it in the XY. So the camera for game face was face on, and they get the person moving in what they call XY coordinates. And we've got Vicon. Now, Vicon could be spun around any way, but I know if I calculate speed, because it's vectors, I'll be able to line them up for time. To do that, I loop through to find the best correlation, what's called a cross-correlation technique. And the reason I use correlation in this case is because Vicon is in millimeters and game face or markerless motion capture, the XYs are in pixels. So they're not in the same units at the moment. You'll see later on I do other analysis where I roll through and get a root mean square error. I can't do that in this case because I'm using different units. So I use the cross-correlation technique. Once they're aligned with the speed, so I've aligned them in time, then I do spatial alignment. So what I do is I again rotate Vicon data in one plane first of all. So I might do that in the XY plane, and I find the best correlation again. And then I tilt the data back and forth to find the best correlation. So that's how I rotate and align them in space. So I guess there's my analytics that I do, but that's just to clean and align the data. We then look at things like the root mean square, or sorry, the standard error of the estimate, etc., that I'll talk about more in some of the other projects. I just didn't want to have too much repetition. Another company that then approached me when they found out that I was doing validation on markerless motion capture was a company called VuMotion. I think they've been quite successful, actually. They're an Australian company, but they do sprint analysis. Initially was the work that they do. And I think they've actually moved into the American market. So you may have heard of them. But this one was a slightly different project that we undertook with them. And it was looking at single leg performance, single leg hopping performance in relation to the high incidence of ACL injuries that we have worldwide, certainly in Australia. Within women's sport, it's a major issue. In Australian rules football, for example, on average, one woman goes down every single week in the rounds with an ACL injury or does their ACL. So they play one game a week in the AFL. And it's the same stat for our National Rugby League for women as well. So I'm sure there's probably similar stats in America with the high incidence of ACL injuries. So it's established that it is a significant problem, both nationally for us in Australia and globally. Within Australia, estimated to cost up to $300 million alone in missed games and surgeries, etc. There's extensive research on ACL injuries. If you go to a Google Scholar search on ACL injuries, there is a huge volume. It's been a massive increase in the volume of research on ACL injuries. Are we learning? Are we getting any better? Are injuries decreasing? I don't think so. If you look at a lot of the research, it is lab-based biomechanical analysis. So how does that transfer to real-world practice? So what VU Motion and some other, it was actually a group of strength and conditioning coaches and physiotherapists wanted to do was develop some type of accessible single leg function assessment. So there's been other tests that look at hops for distance in a frontal plane, sagittal plane, etc. VU Motion, in conjunction with a physiotherapist and strength and conditioning coach, developed a triple hop test, 3-hop test, that was like a diagonal hop test going forward. And they wanted to look at locomotor performance, look at the coordination of doing that. For example, the contact time, how long they were in the air, how far they went with the hop test, their ability to do it efficiently. And so they used pose analysis to provide a biomechanical analysis of the person doing the hop test. And this hop test can be done in a very short period of time with the markerless motion capture. The analysis can be done within 24 hours. This is more of a cloud-based assessment. It's not on your phone. Get the video, you get instantaneous feedback. You upload the video to a cloud-based platform. It goes through some AI processing and then comes back down and you get your results. But it's a lot more fast and efficient than doing a lab-based assessment and setting up a Vicon analysis. So this was about the time when we set up our new Blackdown lab that you saw at the start with the running track. So Oscar did this project this year as part of his honours, and we did the validation was again collect the VU Motion data during the hop test and data simultaneously. Again, same data processing, and I won't bore you again with all that cleaning, etc. of the data, but I had to align them in space and time. And to quantify the accuracy, we used a stat called the typical error of the estimate. Okay, there was some subtle differences in the way angles are calculated from markerless motion capture and Vicon. And what we realized with things like the root mean square error, we could see there was like an offset, and I'll show you some graphs that do that. Just briefly, again, we clean the data, we split by landmark, we do the same for VU Motion. We synchronize the same, but VU Motion, the difference here is that VU Motion and VU Motion, got game face there, sorry, replicated this analysis, but this is VU Motion. They output a joint angle. So they do the angle analysis for me. I don't have to calculate that. So I've got angle from Vicon. I've got angle from VU Motion. So I could loop through and find the smallest root mean square error as opposed to the correlation that I used before when I was working in pixels. And here we see, this is what we saw with the ankle, both the left and right here. The 2D analysis is in the orange, so that is the markerless motion capture, and Vicon is in the 3D, the blue. And we can see it, looking at the plot, you go, they're tracking each other very similarly. It's just one's offset. So what we realized, it was the way that markerless motion capture tracks the ankle angle as opposed to Vicon. Vicon does a real modeling, etc., and there's some inbuilt analysis that provides the angle of the ankle, whereas we established that pose analysis was doing it slightly different. So knees better, certainly very much kind of looks like it's almost overlapping, some offset slightly, but looks very good. And the hip angle was also very good. So this was the initial analysis that we did. But again, going to some analytics here, the root mean square error we saw was about 5 degrees for the hip and knee, but about 14 degrees for the ankle. But I could see it was tracking right. So what I thought was, well, what I want to quantify is if it's tracking it okay, I want to quantify that. How well is it tracking it, even though I know there's an offset? Now, the problem with root mean square error, it encompasses both any mean bias, any offset is encompassed within the root mean square error, plus the variation. What I wanted to do was extract that mean bias and just look at that variation. So, like I said, there's disparity in how the angle assessment was done. So what I did was what we did was look at the validity via linear regression here to extract the mean bias and then establish the residuals when we get the offset accounted for. So I could see there was actually a mean bias at the ankle of about 14 degrees. So that was okay. I wasn't too concerned about that. What I wanted to know was this stat, was the standard error of the estimate. So we fit our linear regression, we get our prediction equation, we fit our line, and basically the line difference to the line of identity, or the line of, where we get the perfect agreement, that offset, we can see there's an offset, but what I want to do is say how consistent is that offset? And that's where the residuals and the standard error of the estimate tells us how well the markerless motion capture is tracking the ankle angle in comparison to Vicon. And what we saw was that when we did that, we got about a 4-degree standard error of the estimate for each of the joint angles. So pose or markerless motion capture is tracking each of the angles in a similar way. It's just our ankle seems to be offset, but it is tracking it within 4 degrees. The stats that we had to do was a linear mixed model to account for that we have multiple participants, and participants have done multiple trials. So it's not just a standard linear regression. We had to do a multiple linear mixed model to account for that, to extract the standard error of the estimate. Going back to this sprint analysis that VuMotion have done, and I've currently got a PhD student working in Australia. We have industry-based PhDs where the industry co-funds the work that the PhD student would do. So we were lucky enough to actually get a government award here to do a joint PhD with VuMotion. What we first wanted to do, this was the sprint analysis. Well, probably the most important thing to establish is, are they accurately tracking the speed of the athlete when they run? So that was quite an easy one to do, where they could set up their camera and video the person doing the sprint and do all their pose analysis. That they have a closed source one that's up in the cloud, but it outputs a speed trace of the athlete. I am lucky enough at ACU that we've got a laser system, basically similar to the device that police use in Australia to check that you're driving at a suitable speed. But laser samples at 1,000 hertz basically sends out a beam, it bounces back, high sample rate, we can get a very accurate measure of speed. Well, our first analysis showed that their root mean square error for assessing speed was with about 0.1 meters per second compared to the laser. Now, when we look at team sports have a speed range of about 0 to 10 meters per second. So that's an error that we say is about 1% for team sport athletes. Different if you were looking at Usain Bolt, who used to run at 12 meters per second, slightly different there for him. But team sport athletes will get up to about 10 meters per second. I know your NFL players probably go a bit faster than that. That's okay. Stride parameters. So the next study that we did with VuMotion was assess their stride parameters. Now, stride parameters are things like contact time, flight time, step length. Okay. To do that, we didn't want to do it in the lab. We needed to use a different system. There's a system called OptoJump that's commonly used both in scientific research and within practical settings. And it is a beam or two tracks that you run down beside the track here. They're little interlocking yellow modules, and it sends out an infrared beam across the track. And as soon as the person steps on the track, they break that beam so it can work out where they are in space and how long they're on the ground and how long they're off the ground. And we found that the markerless motion capture was able to look at stride rate and stride length with a mean bias of about 3%, a standard error estimate or typical error estimate of about 6%. Contact and flight time, very accurate, slight variation with the standard error estimate being around 3%. And then the next study that we're going to do with that is look at our joint kinematics, our hip, knee, and ankle angles as we move forward. And that's going to be Louis' PhD. So that is to come in the coming years. The processing of the data, again, we just have to, this was quite simple. OptoJump's quite good. It just outputs all your parameters for you. The VuMotion data, again, they output all their parameters. So this was a very simple study that we just had to basically align by participant trial and contact time. Again, we used our validity by linear regression, so establishing the mean biased and the standard error of the estimate. And we also worked out the limits of agreement. And it did a linear mixed model, and this paper's been submitted. So like I said, the standard error of the estimate for your stride parameters, contact time, flight time, and step time is both of those combined. We're looking at an error of about 0.005 seconds. You'll see flight time is slightly less using markerless and contact time greater, but we think that is a difference again with the system, and that OptoJump is about 5 millimeters off the ground. So it's going to have slightly longer contact times and shorter flight times compared to the markerless motion capture. Another area that's but rapidly developing in Australia, and I'm sure this is the same in the States, is the use of AI to kind of assist with healthcare and rehabilitation. So this is a rehabilitation application that's been developed by a company called Medical, and it's looking at people after they've had osteoarthritis surgery and getting them back on their feet and getting moving. In Australia, very hard to get physiotherapy and what we call exercise physiologists in the hospitals. You know, each person that's undergone surgery might get 15 to 20 minutes with a physiotherapist or exercise physiologist per day. What about if an application can run them through their rehab at a faster rate? So it's a big area. It costs us in Australia, it's a $1.2 million industry, this osteoarthritis. They have a lot of initial therapy, but we need there was an increase accessibility is what we're really looking for. And so this Peak Medical created the better in, better out application using markerless motion capture. And again, they approached me and said, well, we need some validation before this will be taken up. So that is the other one that we're currently working on. We've collected the data and we're currently processing that. And just yesterday, we got what they call a New South Wales government, and that's the state that I live in, New South Wales government funding, that they're going to match dollar for dollar the money that we put into this research. So they've seen the benefit of it. So that was a good win that I got an email about yesterday. Just briefly, because I know I've only got about 5 or so minutes left, is I want to talk about the FIFA project. And this has probably been the big win for me over the last 8 years. It's, again, the analytics is not that complex, but FIFA is a big company, and this whole area is quite big. So they developed a quality program where they wanted to say, how accurate are the tracking systems that are used in football throughout the world? It is a huge multi-million-dollar industry. The contract for the Bundesliga in Germany for the company to come and do all the tracking of each game is about $60 million. Okay. And that there's multiple leagues throughout Europe, everywhere. And obviously I think the next World Cup's going to be, there's one in Saudi Arabia, just got announced for, I think it's for 32. So big money in tracking. But how accurate was it? FIFA were like, we don't know how accurate these systems are. They could just be making the numbers up. So they came up with a certification process. And this tender was released in 2016 to universities to say, how would you assess the accuracy of tracking systems? We applied for it. We won it. And to be assessed and be certified, companies pay FIFA 20,000 US dollars to come to a test event and get assessed. So far, we've assessed 30 companies have been certified. And that's been a combination of global positioning systems, local positioning systems. But obviously, this talks more about the AI, and AI is used in the camera-based technologies or the combined ones where they use camera and LiDAR. Global positioning systems, local positioning systems are wearable devices. The data gets spat out. There's no AI processing in that, but the camera systems certainly do. This one's a big setup. We need 40 Vicon cameras set around the field. We get a 30 by 30 meter capture space. We get up to 4 million data points per test event that we need to step through and process. And we provide a report to FIFA and the provider on their accuracy. And basically they get a analysis and a tick the box. There's a bit of a setup of the Vicon, and here's the markers on the player. They get on the shoulder, 2 on the hip and 2 on the back of the hips. We do multiple movements within the space, a little circuit where they run around, and then we play some games in that space. And then they also sprint through that space because we need some high-speed running to see how accurate they are at the high-speed running. Lucky for me, I've been on fields such as the FC Barcelona. I'm not sure many soccer followers here. I'm actually not a soccer follower myself, but this is big to get on that field. So big that when you walk on the field, you have to step in some soapy water and then get your feet, shoes blown dried so you don't transfer any bugs onto the field. So that was quite an experience. The process, again, it's a cleaning process. I've got to clean the Vicon data we collect, import it, extract the XYZ coordinates of those markers, calculate speed, and we say it's the speed of the center of mass. I filter it. We use a 4th order low pass Butterworth filter with a 1 Hertz cutoff. That's kind of the industry go-to in regards to filtering speed of people in team sport athletes. Then I'm clean the manufacturer data, and it comes in this is the hardest part. It comes in all different formats. They send me text files, DAT files, CSV, JSON files. Learning a JSON file, that took a lot of time. If anyone's really good at JSON files, let me know. I need your help. I struggle with them. Timestamps, that's the other one. They all use different timestamps. UTC time, how many centiseconds since 1970? Dealing with timestamps is a massive issue for me. We use a 3-point central method to calculate speed of their data. They provide speed, but they may have used different filterings, lag, lead filters, etc. So the speed might not line up. So I have to calculate speed myself, and I apply the same filter. We downsample Vicon from 50. We upsample their data to 50, so we've got a consistent match. And then we export. I time synchronize that data. Again, I bring the data in, I merge it together, and I roll it through a loop to find the minimal root mean square error. And I visually check every individual file to make sure I've got an alignment. Here, I've got an alignment. You can see vaguely, there's a slight difference in the data. There's a black and a blue line there, but you can see that is a match. That's a match for speed. Okay, you can if you don't get a match, it stands out straight away. So I can tell manually that I've found an alignment between the data, and I get that misalignment by the manufacturers called the wrong player. Red 23 was called white 23 or something, and that causes an issue. They've got the wrong session or something when they've detailed their data. Then I can spatially align it using a similar method to what I did before with the markerless motion capture, rotating the data. Luckily for me, we're only working XYs on this project, so that saves me a lot of time. So we're only working XY coordinates. So I rotate it through 0.01 degree alignment, and then I shift them to overlap. And you can see here, this is the type of data we get, where the red is the manufacturer, blue is the Vicon. You can see that they're closely aligning. They've got an error here of about 0.41 meters. Their speed is about 0.11 meters per second root mean square error. I then combine all that data, and surprisingly, I'll put it into pivot tables in Excel and send it to the other group, because the great thing about Excel is that everyone has it generally on their computer, as opposed to things like Power BI or developing Shiny apps, etc. Everyone can use Excel, so it's just an efficient way to link the data. And there's a bit of a screenshot of I do this for one manufacturer. I send them, we have one file, and everyone in the group can manually go through and just check each of the drills by player. We then provide reports and stats analysis to the providers. And then we've got a ranking system where FIFA sets a standard. And this is an ever-changing standard. So based on industry, whether you're above industry standard, at industry standard, or below, obviously as things are improving, they're getting better and better. So they need to get better and better to stay up with what we call the industry standard in regards to tracking. Just to finish, the latest project that we're doing in this tracking space is not using what we call camera systems that are set up, fixed cameras. We're using what we get off the TV, broadcast. So companies can use broadcast footage to track the players. And it is actually surprising how accurate they can do it. And so this is how rapidly the AI is developing. They're tracking the players, they're tracking the ball purely from what you see on your TV. Obviously, there's times when the player's not detected. They're not in the camera. They use AI to predict where they are. And even that is quite surprising. So this is root mean square error for speed. Even when they're not in the camera, just predicting on where they were and where they went to between the camera frames when they could visualize them, they can track them within like 1 meter per second squared. When they are in the footage, this is just different companies that did this project for us. We can see that they're quite accurate. 0.35 meters per second squared for a root mean square error from a camera that is not even fixed, it's just moving, is quite impressive. So this is one of my PhD students has done this as a project and is just about ready to submit this one. So a couple of minutes over time. Sorry, Dave. Hopefully I got some analytics in there, and there might be some questions that arrive. But basically that's the work that I do. Thank you for your time, and I'm happy to take any questions.
Great, thanks, Grant. Certainly lots of analytics for us to digest there. So let me open it up to questions here. Sort out. So if you want to just raise your hand, virtual hand, and unmute, or when I call on you, unmute and ask your question, that'd be great. So please don't be shy. We've got a few minutes here, so. So while we're waiting for others to ask, yeah, like I didn't know you had secured that FIFA project. I'm sure that was probably a very competitive process. And how did you come up with the design for the validity study? Like, and
this is actually it's actually an interesting story. So when they put the first tender out, they said they had real specific criteria that they wanted. They said that it had to be full field. It had to be done within games, and it had to be multiple games with every single player on the field. Now, we knew straight away that wouldn't be the correct way to do it. we needed to use Vicon, and Vicon doesn't have the capability to do full field, to do a game, etc. Like they specified the referee had to be on the field. So the reason we won it was that we took a different path in that we used a computer vision AI system that we'd validated against Vicon. We said we will use that as the criterion because we've validated it. At that time, there was no other computer vision that had been validated. And we were we were the only group that met the tender's criteria because my understanding is the other universities and other groups that put in for it said they had to use Vicon. And the brief was, no, they don't want to use Vicon. They want to use full field. We then did that study. And when we presented the results to industry, etc., and sat down with FIFA, they questioned, while you're using a computer vision as your criterion, you need to use the gold standard, which is Vicon. So then they said, oh, can you do Vicon? And we said, yes, we can do that. And we've basically kept the tenor. So we got it by not using Vicon in the initial part, and then we've continued on now with Vicon. And lucky enough, we've got some experts in the group, Kev Ball down at Victoria University, just access to the equipment. Like each of those Vicon cameras is worth about $25,000 is my understanding. Even the tripods are expensive, and to have all that equipment and ship it across the world is quite an expense.
Yeah, no doubt. So with these different applications that you showed, you know, the sprint analysis, the tennis swing and whatnot, like what kind of information insights are you getting into performance from those at the current time?
So there's two kind of directions it will go. It will go, like I said, these are companies that are developing applications, and their whole process is to make money. We know that that's what they're trying to do. So the information and feedback that they provide is different to the scientific biomechanical analysis that a researcher might want to have. So if they're smart, they have both. They have the stuff that the end user that has their little camera and has paid their subscription gives back. So a sprinter, someone might want to look at their sprint technique, set up their camera video themselves, and then get feedback. They'll just want to look at things like speed, contact time, flight time, etc. They might not need all the joint kinematic analysis. But if you're a coach or you're a sports scientist working with a sprinter, then that detailed analysis of the joint kinematics, for example, would be of interest because you might want to track that over time, implement some type of training program. What are the standards? So let's get a couple of the world's best sprinters, do an analysis on them, and because that hasn't been done. They don't get assessed you're not going to get the world's best sprinters in a biomechanics lab and get a full biomechanical Vicon analysis of them running over 100 meters because it's just not going to happen. But with this markerless motion capture, we can do that. So there's certainly scope once my PhD student's Louis, once he's validated it, then if we can access elite athletes, that biomechanical analysis can become research projects. And I think that it can be published research because if you can get top quality sprinters and do that type of biomechanical analysis, that is useful information. So they're the two kind of streams that I think it can go down. Basic end user analysis, scientific research-based analysis.
And do you know just sort of and Carmen, I'll get to your question next. What's going on, or is there much going on with goalkeeper analysis? I guess in soccer or any, I mean, in the rugby codes, they wouldn't have it, but do you know of any applications where they're using the footage to analyze goalkeeper performance?
Not that I know of. Are you talking more in a competition or a training environment, and what type of What type of analysis would you be
Well, just any,
thinking of?
well, exactly, right? Like those are all open questions and ones that
Yeah.
aren't being explored. Just, and I'm thinking like in Canada here, we have, ice hockey is our major sport and goaltending is, critically important. The teams that go to the championship finals almost always have a top flight goaltender. And
What's
yet,
goaltending? Sorry, I
well,
don't.
it's goalkeeping, like in soccer, same thing.
Okay.
Yeah, so goalkeeping, same, synonymous.
Yeah.
And it's a super technical position. Um, and yeah, I don't, to my knowledge, there's really not very much in the analytics space, but you could imagine how computer vision and this type of biomechanical analysis that you've discussed today could be applied to analyzing the movements of goalkeepers, their positioning, setting up for shots, reaction times, all sorts of applications.
Yeah, certainly. I think that there's the two applications there that you'd get the in competition analysis to see what they do. And the great thing about ice hockey, I think you call it, as opposed to
Yes.
field hockey that I'm used to, is that
Yes.
you
Sorry.
could certainly get cameras set up, I think, that could focus in on the goalkeeper.
Mhm.
Then in training, you could obviously set up cameras, etc., that could do that same type of analysis. So that certainly would be something I think would be useful. The other thing that comes to mind when you're talking about goalkeeper is the eye tracking.
Mhm.
So we have systems that we can track the eye where the person's looking and what they're looking at. I think that area is developing rapidly where you'll be able to have goggles on that have a camera that goes out to give you what the person is seeing, but then at the same time has a camera looking at their eye and tracks their eye and then overlays that on the footage. So you can see the video footage of what they're seeing, but a dot represents where they're looking at. So you'll be able to get that information on experts in the future. That might happen in competition.
Yeah. Awesome. Thanks. Carmen, do you want to just unmute and ask your question?
Sure. Hi, Grant. Nice to meet you.
So,
I'm a fellow strength and conditioning coach as well. So I'm quite familiar with the motion. In fact, doing a little bit of work with Sam Portland right now, who's in the UK, he's a speed coach. And we had a meeting last week just talking about sort of this space. But just I want to get more clear on just from your perspective. So what I understand is that view motion quantifies joint position, but it doesn't give any. And you keep using the word analysis, and when I think of analysis, I think of it's good or it's bad within like a technical model. So it's these applications, this technology is really giving this quantification of joint motion position, but without any information for the practitioner as to whether or not the performance is within a technical model. Like that would be up to me, the coach, correct?
yes, I
Okay.
think I'm actually doing a paper at the moment. It's more of a coaching paper. We're just trying to work out where we're going to put this one. I think maybe Strength and Conditioning Journal, more the coaching one. So they use the VU motion analysis to look at. It was just adolescent athletes actually within a school that did some speed training and tracked them over time. And the person that did it, a colleague of mine actually, and he's more of a sprint coach, strength and conditioning coach. He talked about, I think it's like things like switching and positive running, etc. But so I think that kind of is what you're talking about, where it's providing, well, do they do certain things? Is the athlete doing certain things rather than just giving them an angle, etc.? It's how good are they at this component that we think is important for sprinting. But I'm no sprint coach, and I haven't done a lot of work in sprinting. But I would say that there'd probably be a bit of variation in what different coaches think is important in regards to technique. That said, reading through this paper that we've done, I think there's some fundamental things that they need to have right. And I think that's what markerless motion capture is moving towards. And Dave asked that question before. You think about the end user. If you just want to look at your sprint technique, you don't want to know the actual joint angle or number. You might not need to know that. You just want to know, well, what do I need to work on? Oh, you need to, I don't know, excuse me for my simple terms here, but you need to get your knees up more at the front, or you need to spend less time on the ground, or you need to be more upright with your position or something like that. They just need it put in simple terms.
Great. That's helpful. Thank you, Grant.
No worries, come.
Thanks, Carmen. I'm going to go next to Katie.
Hi, Grant.
Okay.
Thank you for the talk. It was really interesting. Is it okay, Dave, if I ask two questions? Okay.
Yep, go ahead.
One is a little bit more bigger picture question. I'll give you both questions. So one is a bit more bigger picture. So I'm curious how you establish these connections with these companies, with these sports organizations, but also with the health organizations. So it seems like there's a pretty there's a lot of applicability for this in various kind of avenues.
Yes.
And then you also discussed, or what was brought up was eye tracking, for instance, for goalkeepers. And I was considering the feasibility of this because, so in my lab, we do eye tracking. I don't do eye tracking in my project, but some of my lab mates do. And the goggles that we use can be quite fragile. And so when you're thinking of goalkeepers, it you're not we do walking in our lab, and so the probability of getting clocked in the face with a ball is probably going to be 0%. But when goalkeeping, so I was just curious about those two, and I don't know how much information.
Yeah, okay. So how I established links, I've been lucky where they've kind of approached me. I think it started with, I think the game face, the tennis one, that came about because they were actually looking at player tracking in team sports and potentially were going to go into the FIFA project. And they were looking at that, but then they shifted their focus and they just knew I was doing some work with all the data processing and validation. So they just reached out and said, hey, would you like to do an initial project? They actually got bought out by, I think, a North American company for about $43 million. So unfortunately, I didn't see any of that money. But they approached me for that one. Again, VU Motion, that was... they needed someone to do the first validation on the speed. And that, for me, that was, and this is where I like to work. I did that almost as an in-kind contribution for them. I didn't ask for any money. I just said, we can do a quick session. It'll be one day, come down, we'll get some athletes. They'll run through, you do your video analysis. I'll get the laser there. We'll do some basic analysis. And they were like, fantastic. And this is where I guess these things come back to reward you. That was an in-kind contribution that I did for them. They then, when I approached them to apply for an industry-based PhD government grant, we needed the industry partners to say they will provide $10,000 annually for the 3.5 years that the PhD students there. I just needed a letter of intent from them when I put in my application, and they were like, yep, we'll put that. We're happy to do that. And we got rewarded one of those grants. Again, the Peak Medical one, that was word of mouth where they approached me to do some validation. Then we said, well, we'll apply for this tech voucher. I estimated how much it was going to cost to do all the analysis. And then we approached the government to get the dollar for dollar matching, and we were successful with that. So it is a bit of word of mouth. I haven't aggressively gone out to any industry partners yet. I'm trying to probably do that more now. And then I see the benefit, and my university is really pushing more for industry engagement. So hopefully that answers your first question. And if there's any American companies or North American companies that are interested, feel free. We could do some collaborative work. Eye tracking, yeah. I could imagine almost ski goggles would be needed for the ice hockey, and even the soccer. It would need to be. I know the basketball players sometimes wear those type of goggles. So as technology develops, the initial iterations of that eye tracking, they were a big headpiece that you used to have to wear. They've become more sophisticated and smaller, but I'm sure that there is potential to change that to fit more of a robust goggle type system. And given the I guess way that Canadians love their ice hockey, perhaps you should approach a company to see if they want to develop something, and if you've got the technology to validate it at your lab, you might be able to set up an industry link, and then reach out if you need any help with the analysis.
Yeah. I was just so because the glasses we use are like quite expensive, so if they were damaged, then you're kind of SOL. So I was just because they have gotten quite small. But I'm only familiar with one company that does like that makes eye tracking goggles.
Yeah, it certainly sounds like an interesting area, and I'm sure that's the other aspect is with the player tracking that we're seeing in soccer, football. At a recent event, we tested a company, and basically they can replicate an avatar of the player. Like the delay was about 2 or 3 seconds. So we were on the field and the players were moving, but they had a cartoon kind of avatar up on the big screen that was replicating the players moving around. And so if you think about that, the potential that at the next World Cup, when tickets are ridiculously priced and people have got to fly to the country to go. Oh, it's actually in North America, isn't it? It's just
easy for
people
us.
have to, So for me to travel, it's a quite a big expense. What about if they could replicate it so you could be interactive? If they can recreate all the avatars in space, could you then subscribe and pay a ticket to be on the field in virtual reality? And it gets replicated. So when they're lining up for their penalty shootout, you can be standing on the sideline in virtual reality and subscribe to that. Imagine $10 to do that, and they get 100 million people worldwide to subscribe to that. It's a pretty good money earner. So that space is certainly developing as well.
Wow, that's quite an idea. Okay, well, we're at 10 after the hour for us, and I think, Grant, you have to get running to your class, so we're going to stop the recording here. But before I do, I just wanted to thank you very much for an interesting talk, and good luck with all your projects.
No worries at all, and feel free to reach out. Any collaboration, my university loves any international collaboration. Always need help with my analytics, so yes, please reach out. I'm sure Dave will pass on my email to anyone that's interested and wants to get in touch.
Yeah, well, maybe we should touch base about your sports analytics certificate, and we've got lots of students who can kind of do the stuff you maybe don't like to do as much. So I'll reach out to you offline here.
No worries at all. Thanks for the time. Much
All right, take care. Bye, everyone.